CEDA virtual distinguished lecturer series. It is, so good day, everyone. Good morning, good afternoon, good night, depending where in the world you are. I hope you're all doing fine. It is my great pleasure to host this distinguished lecture talk by Professor David Pan. So he is a very well-known person in the EDA community, and he doesn't require any introduction. But just to do my job, I will briefly introduce him. So he is the professor and holder of Silicon Labs Endowed Chair at University of Texas at Austin. His research interests include bidirectional AI and integrated circuit interactions, electronic design automation, design for manufacturing, hardware security, and CAD for analog and mixed-signal ICs and emerging technologies. He has published a lot of papers. Many of them received the Best Paper Awards and recognitions in major conferences and journals in our community. He been also very active in the community by being on the editorial board of several journals and the conference committees. He is recipient of numerous awards, Best Paper Awards, top 10 author awards in the 5 decades of the DAC, and ASP DAC frequently cited author awards, and so on. He is also a very good mentor and an excellent mentor. So many of his PhD students and graduate students have received numerous awards in the field. He is also a fellow of IEEE and SPIE. So without any further ado, I leave it to David for his very interesting talk.
Okay. Can you hear me, Madi?
Yes.
Okay, great. Thank you very much, Madi, for your kind introduction, and it is my great honor and pleasure to share with you some of my group's recent results and also my views to close the virtuous cycle, between AI for IC and IC for AI. So as we all know, I think there's not really any introduction, but just to complete the story, right? We know AI is a very hot topic, and there's the ABC behind is the algorithm, a lot of data, and also the chips, right? Which we, as a CEDA and this community have been working a lot, how to design the, better chips, right? So the AI chips, including CPU, GPU, ASIC, FPGA, and most important, dedicated AI accelerators, right? So, but if we look at the nanometer scale chips, right? People are now talking about 5 nanometers, 3 nanometer even, right? So, and you can have billions of transistors, right? This is a very big SoC from NVIDIA. And usually to design such, big chip, right? You usually need to partition them and to do design closure, right? But even 1 to 2 million partition to do very detailed backend iteration for timing, power, PPA, all kinds of iterations could take several days. And now we are even talking about the trillion number of transistors, right? Not quite chip, but the entire wafer is a chip, right? From this Cerebras, a startup company. And what you see at the design, usually you have different masks. However, it's not necessarily what you will see in the wafer, right? And you have to do a lot of mask synthesis, massage the mask such that the final printed image looks closer to what you intend to print, right? So that's why you can see it's a really, really complicated problems. And so modern IC design and manufacturing, has a top-down flow from system level, architecture, logic, and then physical and mask synthesis, verification, and so on and so forth, right? But even for physical design, it has many steps, such as floor planning, placement, and then routing, etc., right? And in terms of manufacturing, so you may need to do, some kind of test pattern and extract the lithography model and so on and so forth, and design rules, and then you have all kinds of, this kind of mask synthesis, etc. And then you send to the fab. But if the fab finds, oops, you test your chip, it doesn't work, you may have to go back and change your physical design, or even you have to change your, architecture. Right? So that's why nanometer design has tremendous challenges to meet all these design requirements, such as power performance area, or well known as PPA. And then meanwhile, you have manufacturability, yield, reliability, security. I mean, you keep on adding to the list, right? And last but not the least, the design cost is really, kind of also following the Moore's law, ironically, so it's getting more and more expensive to design a state-of-the-art chip, right? So that's why, a couple of years ago, DARPA, actually 2.5 years ago, DARPA started this ERI, Electronics Resurgence Initiative. And under that, there's a program called IDEA and POSH, essentially tries to develop the next generation silicon compiler 2.0. And the DARPA's grand challenge to the research community is whether we can have something like no human in the loop, 24-hour turnaround time, right? So then the key question is that, it's a really big challenge. And with the recent advancement in AI, right, can AI help? And if so, how, right? So it turns out that actually AI indeed can help. There are two aspects, between AI and IC. So on one aspect, right, so we can leverage a modern, AI hardware as well as software, so that we can design better, EDA tools and design methodologies to enable agile and intelligent IC design, which can even, probably outperform the current tools and achieve design, equivalent scaling of Moore's law. Because we know that, current tools, this top down with so many abstractions, there are definitely a lot of optimization, performance left on the table, right? And then on the other hand, there's also a lot of, customized IC accelerators for AI. So interestingly, if you look at the Moore's law, right? Moore's law essentially says, oh, the number of transistors will double every 18 months or something like that, right? And the number of machine learning papers, which basically AI papers, also actually follows Moore's law or even beat Moore's law, right? So that's actually quite interesting. So if we can kind of closing this AI and IC loop, we will have exponential times the exponential or exponential to the exponential, right? So anyway, so you can imagine where the blue sky, right? So in the rest of my talk, I will share with you some of my group's some recent work in terms of AI for IC and also some IC for AI. So in terms of AI for IC, I'll show 3 case studies. The first one I will show is this Dreamplace, which actually we collaborated with NVIDIA research. And it stands for Deep Learning Toolkit Enable the GPU Acceleration for Modern VLSI Placement. Actually, we had a great honor. This won the Best Paper Award in DAC 2019, and we also had a lot of enhancement, and which was published in TCAT. So we also made this source code available, and it actually has got many stars, and many companies have been using this Dreamplace to my best knowledge. For example, NVIDIA, of course, our collaborator, and also Google, and among others. Right? So we know that placement is a classical EDA problem, and even ever since we started to design chips, right? We have to place the chips, and the modern chips you have to place big macros as well as millions or tens of millions of standard cells, right? And this plays a central role, I would say, really central role in IC design closure in terms of quality of results, power, performance, all this, right? Because placement is in the middle of this design step. And it determines interconnects, right? Because if you don't place them, you don't know how long your wire is, right? And we know that for nanometer designs, interconnects, compared with transistors, right, is not scaling well. So that's why it dominates the overall power performance area. So since placement is such a classical topic, right, I won't show all these details, but from 1970s, we do like, partition, simulated annealing, etc., right? Later on, we do, like a Gaussian kind of partitioning and a quadratic placement. And then modern days, actually, state-of-the-art placement usually follows some nonlinear placement formulation. Essentially, you can think about, oh, I want to minimize the total wire length, right? And this E is like, as long as there's a connection, and you have XY location for the cells, then you want to minimize the total wire length. By the way, this you can also make the total kind of weighted wire length. You can set some weight in front of it. And think about for timing critical nets, you give it higher weights, otherwise lower weights, right? But the problem is that if you just want to minimize wire length without constrain the density, that won't be very interesting, because then all the cells on top of each other, you say, hey, I have wire length 0. That's not meaningful, right? So to make this kind of constraint optimization, usually people can change the formulation into some kind of unconstrained optimization. This lambda is kind of like a random multiplier, but you have to iteratively change them, and there are many, many details I won't be able to show. But this kind of effort is a huge development effort, and it takes a huge amount of runtime to write a really state-of-the-art placement engines. And think about it, you are talking about millions or tens of millions of standard cells, right? And also placement is such an important problem because it will be called many, many times, maybe to adjust the weight for timing, and then to maybe artificially inflate some cells for congestion and the power and so on and so forth, right? So what's your dream place, right? So the dream placement engine, you want to get the best quality of results really, really fast, right? Because you may have to run it so many times. And also, maybe you will think about some smarter placement algorithms and so on and so forth. You do want to develop a new placement engine really fast and make it extensible and so on and so forth, right? So, nowadays, right, for 10 million cell placement, right? If you don't, before our dream place, it could easily take hours, right, to run a really large scale placement. Our dream is that, hey, can we do it in minutes? So actually, our motivation also is a connection with AI is motivated by the recent, really this advancement by deep learning in terms of both hardware and software. So thanks to deep learning, right? So and because of all this training, it turns out that the GPU really, compared with the CPU advancement, they don't grow that fast, but GPU really, has done in terms of training and all this has tremendous advancement. And that's why actually nowadays NVIDIA, in terms of market value, is much bigger than Intel, right? Meanwhile, right, there are tremendous deep learning toolkits which are open sourced by different, big companies like Facebook and Google. Right? Google has TensorFlow, right? And Facebook has PyTorch, and among others, right? So there's a huge community of software developers trying to make those toolkits really, well-tuned, well-optimized. So then our Dreamplace, strategy or kind of motivation is that, hey, can we make some analogy between nonlinear placement optimization with neural network training, right? Then we can greatly leverage those deep learning toolkits in terms of software and also the hardwares. By the way, in our application, we use the GPU, right? But think about it. Okay, if you have TPU from Google, or you have your even own dedicated accelerators, hey, we could use that to solve placement problem, right? And then they can enable really fast parallelisms and acceleration while getting state-of-the-art results. So what's the analogy behind? So as we know, right, when we do deep learning, and usually you have some data instance, you will have some label or your target, right? This is your instance. And then once you have a neural network, you will need to train it, right? So you have to train all the weights, right? And through the forward propagation, you can compute the error function, with respect to your label, right? And for example, dog or cat, but it can also be a more continuous value. And then you compute the error, and then you can do a reverse, a backward propagation, and through the gradient and or the weight. Then, by doing this forward and backward propagation, ultimately you can get the best trend network with the best weight. And to avoid the overfitting, you can also add a regularization function, into your objective function, right? So this is a very, classical neural network training problem, right? How do we solve it? Actually, now let's look at our placement problem. You want to minimize wire length and subject to density constraint, right? You want to spread your cells, right, in your chip. So you can think about, okay, I can treat my net as an instance, and my target, let's say I put a target at 0. That means, if I have a error function becomes the wire length, right? And meanwhile, your like a weight becomes your XY location, right? So your XY location is what you need to train. And you can do a forward propagation with the current XY location. You can compute the wire length, which is a weight function. And meanwhile, you do back propagation. You can compute the better XY location. And also, we have a regularization function. Essentially, you can think about it as the density, right? So that there's a really nice analogy between these two. So I have to say that in our Dreamplace, we don't have a lot of training data. We just build some simple network. And essentially, we are using the hardcore solving engines from modern deep learning toolkits and the hardwares so that we can speed this placement tremendously. So that's why we will leverage those mature and highly optimized deep learning toolkit. And meanwhile, which already has a lot of nonlinear optimizers, automatic gradient computations, and so on and so forth in Python, in CUDA, etc. Right? So what we do is that we will stick a placement API, right? And meanwhile, we do need to customize the wire length compute operators and density operators, right? We do some optimization here, right? Because of the time limit, right? I won't show the details, but we also, we can use, the existing different optimize there, but we also implemented this Nesterov method, which is widely used in nonlinear placement, and we try to match replace result. And so compare with the previous academic state-of-the-art placement engine, replace, right? So we actually can, this is of course running on multiple GPUs with 24 cores. And with Dreamplace, we only have one CPU to read in the designs, but most computation is done by one NVIDIA GPU. And so we actually, because we try to match the algorithm, so we get the same quality of results. On the other hand, if we compare the runtime, right? So we compared with the ISPD benchmarks as well as industry benchmarks from NVIDIA. And we actually, found, between 30 to 40x speed up. And so that means, if you have a 10 million cell designs actually from NVIDIA, and it just finished within 5 minutes, and actually replace got stuck even 3 hours, right? So so remember at the beginning we had some dreams, right? So we want to get the best quality of results. We want to have really fast speed and also low development effort. By the way, to develop our placer, right, it just take a couple of months, right? But previously it could take a year, right? Because you have to write all the optimizer yourself and tune these, So it's a non-trivial effort. And also, our framework is very extensible in the sense that, okay, if you get new algorithms, new acceleration innovations, you can easily plug in. So our dreams come true, right? Meanwhile, actually, beyond the Dreamplace, we can even dream bigger in the sense that, hey, we do have many solvers. In our TCAT version, right, we also showed that we compare with the stochastic gradient descent and Adam, those very popular solvers in deep learning toolkits. And we also try to handle roughability and other objectives. And we also, you can also extend it to new accelerators. We only use the one GPU, right? But if you have many GPUs or even distributed and other, acceleration schemes, you can do that. And we can also, extend it to other CAD problems, such as gate sizing or floor planning or macro placement, right? So actually, you guys probably all know the very recent Nature paper from Google, right? So their most recent macro placement, they actually use our Dreamplace, right? So together with their reinforcement learning, right? So there are actually a lot of things which can be done. Here I just showed some example, right? All right, so now let me move on and talk about the next case study of using AI for IC. So I'm going to talk about the Magical. It's machine learning generated analog IC layout systems. As I mentioned, DARPA has this IDEA program, and I'm leading this project under this program. Again, we also have made it open source. You can download our Magical 1.0 at this website. So as I mentioned, right, so Dreamplace mostly focus on digital ICs. We are talking about tens of millions of standard cells, right? But analog IC is a very different world. So usually their design is not very big, a few hundred transistors. They always think, wow, that's pretty complicated already. And so they are still, in industry practice or academia, mostly still, manually designed. It's really tedious and error prone. And the previous design automation effort is not as successful. So there are many, many reasons because they may not be able to handle all kinds of constraints the designers have. And the designers think they have some black magic, right? And anyway, so our magical vision is to develop a fully automated analog layout systems and leverage both human and machine intelligence. So since the launching of this project, we have already published a number of papers on this. So let me actually show you the overall framework of magical. So basically, your input is a certain SPICE netlist with design rules, PDK, and the output is GDS2, okay? And the middle chunk is our magical. It has 3 key, I would say, more technically, interesting components, like layout constraint generation, extraction, placement, and routing. But meanwhile, we also have like a device generator because from the netlist, we can generate parametric P-cells, parametric instance, just to make the entire thing more, standalone and open source. So in terms of the layout constraint generation, placement, and routing, so we do have like pattern matching or some kind of deep learning and so on and so forth, right? But there's also some analytical techniques, for example, placement we have been using. And sometimes we may also need to use some small signal analysis. So because of time limit, I won't be able to show all the details, but this is overall the framework. And in the most recent version that we actually just presented a couple of months ago at CICC, so we also proposed a hierarchical framework in the sense that, with magical, right, you can do block level synthesis, you have symmetric constraint generation, layout, placement, routing, etc., right? But you can also have something called a simulation in the loop, right, with some Bayesian optimization. But one thing that I like to mention is that we can also, not only you can do each of this, small block, right, but we can also consider the top level and integration in a hierarchical manner. And our constraint generation can handle not only block level and constraints, but also, like a more top level constraints as well. So we have actually showed the magical on, for example, this is a small block OTA circuit. And so this is a schematic, and this is a manual layout, which my collaborator, Professor Nanzun, he has tapped out before. And this is our magical layout. As you can see, the magical layout looks very different from the manual layout. And however, if we do post-extraction simulation, by the way, again, as you can see, right, so analog circuit is quite complicated. Right? It's not just like, in digital circuit, you have PPA, right? But in analog circuit, you have DC gain, and some bandwidth, phase margin, CMR, and so on and so forth, right? So actually, since magical can, automatically extract those symmetric structure very well, so we can actually got reasonably good results compared with, hand-tuned results. However, in terms of runtime, right? So this is, as an experience for experienced PhD student, right? Takes like maybe a week to lay out this manually, right? But for magical, it takes seconds, right? And another thing is that, with this, we can actually generate, with changing, we can change parameters, right? For example, the placement weight. So we can actually generate, thousands of, tens of thousands of different layouts very easily. And actually, we even released the open benchmark and open circuit with post-layout simulations, which can allow us to explore many, many different kinds of analog layouts. And which I think will be very useful because there's no way for human designers to generate that many layouts, right? But with magical, we can generate tons of different layouts. And another thing that I'm really excited to report is that we not only have this for small circuits, we recently just tapped out it's a pretty complicated and high performance delta sigma modulator. And so compared with the original paper, which was manually designed, right? So we can actually get a really comparable performance, but everything is done automatically. And so as you can see, it has 3 integrators and 2 DAC and so on and so forth. It's actually quite complicated design. So we tapped out using TSMC 40 nanometer. Thanks for their shuttle program with us. And we actually got a bunch of chips back, and we measured here, as you can see, it's a chip measurement of 8 different chips. And this is one of the representative ones, as you can see, right? So SFDR and all these metrics are actually pretty good. And in terms of variations, it also handled it very well. So basically, Magic does all the placement and routing, including signal routing and the power ground, right, automatically. So and compare with the previous state-of-the-art CT DSM ADCs, right? So these are just some previous ones, and this is our like a baseline because you know, we Professor Nanson's group tapped out this before, and we actually just fully automated that. And one thing I would like to say that, you know, the Magic can also take user specified input. For example, in this case, because usually top-level designers, they know what kind of, you know, a signal flow you would like to have. So we have a signal flow given to it. And then actually, that's the only thing that a user provided, and the rest are automatically generated. So we can get pretty close layout as the manual layout. This is a manual layout. This is our Magic generated layout. So the chip area are all very similar. And if you look at the different metrics, so they're actually quite comparable. So our, for example, FDR is a little bit worse, but our like SNDR is better, right? And in terms of the figure of merit, yeah, no, it's even slightly better, right? All right, so now let me move on to the more design and manufacturing kind of interface. As we know, right, what you see is not necessarily what you get, right? So there's a strong motivation to, let's say, give me a mask. Can you quickly generate, you know, the printed image? Or of course, even with some OPC, the printed image, right? So so it's usually a very, very expensive process, you know. But we actually proposed some framework to do Lithogen by using generative adversary network to do an end-to-end lithography modeling without going through the lithography simulations, right? Because lithography simulation in general, I don't have time to show the details. You know, there's a lot of optics and the photoresist, you know, stuff like that is very, very complicated. Even for a 2 micron by 2 micron area could take a minute, right, to simulate it. However, basically, you know, with Lithogen, we bypass all of that by using generative adversary network. This is a well-known technique, so I think it's one of the most you know, widely known, you know, technique in machine learning community now. So essentially to do image translation, and I won't go into details, but our you know, printed image prediction is inspired by this. And essentially it is an image translation problem. Think about, you know, you have an initial mask, instead of doing very expensive lithography simulation and get the, you know, printed image. By the way, you know, for the modern designs, right, if you want to, you know, print those kind of vias, these are the target pattern you need to print, right? But people usually also need to, you know, insert maybe, you know, so-called SRF and supported, you know, assist features or OPC, stuff like that, to help those features to be printed, right? But this is a very expensive process. And what we do is that we will actually make it into a kind of image translation problem, image translation task, in the sense that, hey, if you want to know, hey, for this really critical via, you want to know what is its printed image, right? So instead of running very detailed lithography simulation, you get this, right? So can we directly, you know, instead of using simulation, we directly through translation and directly get the printed image, right? So we actually generated many learning pairs, and this is generated by detailed litho simulations. And once we have many of these, you know, learning pairs training set, we can build a, you know, GAN, C GAN, which is a conditional GAN. Essentially, a GAN has a generator and meanwhile has a discriminator. I won't go into details, but basically using this kind of GAN framework, we are the first to propose this kind of framework. And it actually can converge fairly quickly, and compare with you know, very detailed rigorous simulations. The Lithogen is, you know, thousands of times faster, and we can get those, you know, directly get the printed image. Yeah. I'd like to mention that previously people have worked a lot on lithography hotspot detection, including some of the early works my group has done, even more than 10 years ago. So there are a lot of work people have done on that, but that is a binary classification problem, whether there's a hotspot or not, right? But the Lithogen is doing much more in the sense that we not only say whether this printed image is good or not, but hey, what it looks like, right? So it is important to have a printed image, right? For example, if you have a transistor, people make slides and know what is the real performance, and then you have a veer and stuff like that. Whether you have open shorts, and so there are a lot of more information with a printed image, right? So with this, actually, I think it can be used to bridge the gap between design and manufacturing. All right, so far I have talked on the more AI for IC aspect. Now let me talk about the IC for AI aspect and to closing this loop, right? So IC for AI has been, I think now everyone has, it's pretty much everywhere, right? So or from the early like IBM TrueNOS, and then to GPU, TPU from Google, it's already like the 4th, 5th generation now, right? And all the phones now have neural processor unit, and so on and so forth, right? Not only for all this, but also there's the FPGA, right? So AI chips are everywhere now, right? But those are all based on the electronics, right? Those are, I would say, conventional transistors, right? So then the question that I would like to answer is like, can we also leverage optics and photonics, right? So essentially by playing with light, right? So this is actually some early work that MIT researchers have done, right? So they showed that you can actually have a optics and photonics IC integrated with modern technology, and then by doing this, by playing with light, actually you can have much better power and much less latency, right? Because speed of light, right? If you can transmit doing your computing through like light speed, right? So after they published their paper in Nature Photonics a few years back, and there are already quite a few startups, right? These are 2 spin-off from MIT, but there are, I think, to my knowledge, 10 or so startups try to do AI with photonics, right? So what's the main principle behind, right? So for the optical neural processor, right? So this is the original paper from MIT, right? So the key idea is like, okay, so you have some light. Let's say you have light in, right? And one of the most widely used operations for machine learning is matrix multiplication, right? Or one of the components will be matrix vector multiplication. So how do you do this, right? So usually if you have to use a conventional computer, you have to compile it and then compute it, right? But with neural processor through optics, right? So you can think about, oh, I have light comes in, and the light can be represented the light intensity or something, right? So then goes through this like a photonic kind of some kind of optical device, right? And this in this case is a bunch of MZI arrays, and essentially you can think about this MZI array is kind of implementing a matrix. This input is a vector, and once the light comes through it, and then the light comes out, is direct a matrix vector multiplication. Okay, so in that sense, so you are using physics and light and optics to do computing directly. But of course, you have to detect the light and stuff like that, and then ultimately convert it to electronics, right? But this part of the computing, you can actually reuse it, and you can. There's many different architectures, right? So that's why they show that once you configure this, the power, the energy assumption is pretty much close to 0. But of course, there's a disclaimer. You have to tune it, right, such that if it is an inference, then light comes in, then light comes out, then done, right? Matrix vector multiplication is done. However, there's indeed some problem. The problem is that the area for this kind of MZI is quite bulky. Each of these devices is quite bulky. Now, when we talk about CMOS transistors, you are talking about the nanometer, right? But when you're talking about those kind of optical device, you are talking about micron or even 10 microns, right? So you are talking about a factor of 1,000 times bigger in terms of area. Oh, actually 1,000 times 1,000 times, right? So this is much, much bigger. So that's why you cannot build very, very big systems, right? But hey, people even now build an entire wafer chip, right? So if there's a demand, if this can show big benefit, right? I think that there's still, you can even do scale up, but still, right? So the area is big. So what we would like to do is to have a software hardware co-design such that reducing area is a very, very important goal, right? Because if you reduce the area, you can actually make a much bigger multipliers, right? So what this case study, this is a paper that we published in last year's SPDAC and actually got best paper award. It's done by first author by my student Jiaqi Gu. So instead of using MZI, right, which is bulky, actually we proposed a new architecture. That's why I think the keyword here is the software and hardware co-design. So this FFT-based architecture, basically, you will directly use coupler, shifters, and those different components. And this one thing that we found that with this architecture, you can do circular matrix multiplication. Again, I won't have time to show the details, but usually, you can do general matrix multiplication. But you can also have some matrix multiplication. This matrix is kind of special matrix. It's more like a circular matrix. And it's not as general as general matrix or MZI, but there are actually a lot of papers even in the mainstream machine learning community, which people have shown that just using circular matrix multiplication, you can actually have pretty good expressiveness and can actually be widely used in machine learning tasks. Okay, so I won't show the details, but basically by doing this with this new architecture plus some software hardware co-design, we actually show that we can reduce the area by like 3x, 3 to 4x, and with various network configurations, and we can get the same accuracy compared with the original MIT paper. And in terms of latency, actually the original MIT paper may be somewhere here, and we actually because in terms of power and latency, we have around a factor of 10 times reduction. So not only that, we have actually extension. This original paper of this SPDAC, we are using FFT and inverse FFT, right? So actually, we found that we can actually, we actually, instead of using this fixed FFT architecture, we can have a more general frequency domain transform. That's why we call it version 2. It's more than FFT, right? FFT is just a kind of special case in this new framework. And so then we don't have to use Fourier transform and inverse transform. We can actually make this both trainable, and then we can have more learning expressiveness and better optimization flexibility, right? I won't have time to show the details. And another thing I would like to mention is that for optics, wavelength division multiplexing is a very, very important concept in the sense that, okay, so people say, optics, your device is like 1,000 times and times another 1,000 than the transistors, right? But optics, you can scale up using how many different wavelengths, because one waveguide, you can have different wavelengths coming into the waveguide. So each of them do separate computation. So in that sense, you can sharing, right? So that's why we can do this kind of sharing. With this new improved scheme, compared with the original FFT ONN, we can get a factor of 2 times area reduction. And also even in terms of the phase shift programming power, so we can get 10x less power. And also it has more robustness when you have phase noise, right? Another thing, because of time limit, I won't be able to show details, right? But basically, right, when you have optics, right, optics is much less mature compared with CMOS transistors, right? So you have thermal noise and so on and so forth. But and that's why you need the software and hardware co-design. Like in this case, when you have more noise, right? So as you can see with our new method, so it's much more robust versus another method, right? So it's actually you will degenerate quickly, right? When you have thermal noise, etc. Right? I mean phase noise. Right? So another thing that I would like to point out again, which is along the line of hardware software co-design, is to as I mentioned in early on, right? You want to play with the light. This is a really new area, so you can have a lot of things to play with it, right? So one thing, one of the key components in the main optical community is using this so-called ring resonator, right? Your light comes in, you can either drop the light or let the light pass. So in that sense, you can think about it's also kind of a transistor, right? You can do a binary decision, but you can also do some other, like analog computing, right? So one thing that we proposed, and we even fabricated some device on this, is to with my colleague at UT Austin, Professor Ray Chen's group. So to do a multi-operand ring resonator. What does that mean, right? So usually, right, this is an operand. It is if you just have one operator, it's controlled by one variable. However, if you have different, you separate them into different of these, and each of them is controlled by some value, and then actually, it turns out that with this single device, you can do some cool stuff, right? You can do a vector dot product. Remember, this kind of, I think now you're familiar with this, right? Matrix and this vector, dot product. Those are very widely used, right? In machine learning. So essentially, with this one device, basically you can do some more stuff, right? So again, yeah, I want to show the details, but basically, right, instead of using single this previously operator, we each of these can have different weights, and you can this MOR arrays, then they can perform matrix multiplication plus some nonlinear activation, and we also have some different rails which can support both positive and negative neurons. Right. Again, I won't go into details, but basically, with this. We can reduce the number of devices compared with a single ring resonator, by a factor of k square, because this k is how many operands you will have for each of these micro rings. But of course, your k probably cannot be too big, because then you have some reliability issues, right? So we found that, for example, 4 or 5 or 6 is a proper number. And then another very interesting thing is that you can then squeeze those, k by k block into one micro ring. And another very interesting thing is that you can also share weights in multi rows. And for one micro ring, you can actually use them for different of these, right? So again, I won't go into details. And there's also further, you can do some software pruning, because we know that for machine learning, right? So a lot of times you can do, a lot of sparsity and, do compression, right? So we can also combine this with this. And so by doing this, we can actually further improve the efficiency. So compared with basically the previous, approach, right? So we can actually get with only single ring, right, not multi-operand, right? So we can actually, reduce the device usage by like 20 or 30x, and so on and so forth, right? We can, with our sparsity control and so on and so forth, we can also have much less parameters and with better noise robustness. Okay. Now let me also talk about another thing, right? So the previous thing, I mostly focused on the, more on the inference side, right? And we try to reduce the area, make your chip more, basically you can, by reducing those areas, ultimately, right, you can actually accommodate to have larger networks. Right? But learning is a very important process, right? So that's why, we want to do, so we want to also have our own chip training. But then there's some problem, right? When you are doing inference, it's just a feed-forward process, right? But when you do training, you need to kind of have some feedback process. And for the feedback process, one of the things is to compute the gradient, right? And but computing gradient is kind of hard. So that's why we use the stochastic zeros order optimization. So essentially you have some forward passing, and then you through this zeros order stochastic optimization. So we can configure the controllers, and then by doing this, so again, you can kind of have this loop so that it can do the training. Again, as I mentioned, right? So through the training, you will have this. You will have this. Oops, sorry. You will have this. You can use the multi-wavelength division multiplexing and so on and so forth. You take advantage of those. And one thing I would like to mention is that with on-chip training, since everything is on-chip, when you have thermal variations, when your device is running, right? So you may have different thermal profiles. And as I mentioned, right, thermal device, optical device are pretty sensitive to those thermal issues. Very interestingly, with on-chip learning, right? So because everything is on-chip, and we are directly using the the real data at that time, right? Your physics will operate in that real temperature. So you have, instead of, for the software training, you have to get the thermal profile and then retrain it. Our training actually has the in situ kind of like a thermal variation directly forwarded to our optical neural network. So we can kind of inherently has a built-in thermal handling, right, for on-chip training. And it's very, very fast. And it's also, can take care of this. Once you train it, you won't have, loss, right? So this is the example, right, we have shown at the DAC last year, right? So for example, if you originally trained using software and then mapped it to a hardware, and because of thermal variations, your accuracy will drop by 6% or something like that. However, with our training, combine the hardware and the software, because it's directly considered in the on-chip training, so you don't have any loss, and so that's why you can get 5% better in terms of training accuracy, right, than the hardware agnostic software training when you map it to hardware. And another thing that this is actually published in this year's AI. So basically, right, previously when we do the training, right, so actually the problem is that in terms of power, right, when you have many things you need to train and tune, that's actually pretty expensive, right? So with this framework, we actually will make basically a lot of this not trainable, right? We will say, hey, if these guys are not so important, we will fix their weight and stuff like that. You only make a small portion to be trainable, and by doing this, and also with some other sparsity constraint, strategies, and basically we can do some hardware agnostic offline training. And then meanwhile, make some of them untrainable during the runtime, during the hardware training part. So by doing this, basically, we found that we can actually reduce the power consumption by further by 95%. So again, I won't go into the details, but this is in the most recent AI conference. All right, so now let me conclude. So in this talk, I have showed how to do AI for IC. I showed some example like Dreamplace using leveraging the hardware and software, and also some game for the lithography, and also the magical for analog analog IC layout, leveraging both human and machine intelligence. And meanwhile, in terms of the IC for AI, mostly I focused on optical or photonic ICs, right? So how we can build ultra fast and light speed and very energy efficient optical neural network and accelerators. And as I mentioned, right, hardware and software co-design is the key. And we have also tapped out some optical chips, which is actually under measurement. So I think there's actually also, this is a very active research areas. So to conclude, right, so remember at the beginning, I mentioned that we want to really close the virtuous cycle between IC and AI, right? So on one hand, right, so modern AI algorithms and also hardwares can help to design better, chip design, EDA, and softwares, and ultimately enable a better IC design. But once you have better ICs, and you can, like GPU or TPU, your AI algorithms can run, much faster, which actually can then help you to design better ICs, right? So then you will have this very nice virtuous cycle. And whether it's exponential to exponential or exponential times exponential, which is still exponential. But anyway, so that's actually, we'll see, right? So we don't know where's the limit, but definitely there's a lot of opportunities for domain-specific hardware, software co-designs. So I'd like to thank all my funding agencies and collaborators from different companies and research groups. Thank you guys very much. And I think we still have 10 minutes for some question and answers. Maybe.
So David, thank you very much for this very interesting and comprehensive talk.
Okay, thanks.
So there are some questions on the Q&A.
Okay, let me take a look.
You can read the question and also answer them. And others, if you have questions, please just write it down in Q&A. Probably it is, I don't know, it is easier if you read the questions yourself and answer them, or do you want me to read the questions for you?
Sure, I can read the question. The first question from AMR, what is the leading database for deep learning machine? I'm not quite sure about this question. I mean, as I mentioned, right, so let me go back to my slides. So there are, yeah, maybe if you can be more specific. So in terms of like, are you talking about, the leading, I mean, nowadays, right, so PyTorch and the TensorFlow are two most popular deep learning kind of framework. What I heard is that, PyTorch is relatively easy to use, right, for my students, right? But both are, these are very popular. Okay, maybe I'll take the next question. So how can we apply AI to VLSI mapping problem? Again, so when you're talking about mapping, are you talking about technology mapping or synthesis? So I think, I know that there are quite some efforts in that. My group also, we published a paper in like the MLCAD, I think this year, right? So essentially when you are doing logical synthesis and mapping, right? So there are many, transforms, right? So you can use reinforcement learning to find, or other kind of learnings to find what is the best sequence. I mean, even currently in EDA companies, right? So there are, there are so many parameters, hyperparameters, right? But machine learning is good to tune all these hyperparameters, right? So you could use machine learnings to tune those hyperparameters, right? Okay, the next question. Do you foresee RL, reinforcement learning, deep neural network, GAN-based EDA tools doing block placement? Already demonstrated by Google. Placement, routing, CTS, optimization, etc., thus making current EDA tools fundamentally outdated. All right, thanks, Sanjeev. This is a really good question. Yeah, I think, all kinds of different machine learnings, as you mentioned, right? Reinforcement learning or deep learning or GAN, or even use the machine learning infrastructure, right? Like I showed for Dreamplace, right? So I think that definitely can disrupt some of the current EDA practice. And Google also, they just showed their macro placement outperformed some, human-tuned placement, right? So yeah, it has been demonstrated for placement and routing. I have to say, yeah, we have done some work for kind of generating routing guidance in Magical, which we call Genius Route. So with some learning data for the, like, let's say, human designed, some routings, we generate routing patterns. But the routing is something, right, which I think still have a lot of room. Right? Routing, when you have very complicated DRCs, right? So how to follow all these, maybe reinforcement learning could do something, or, I mean, this is still something which people, I think still have a lot of room for improvement. Clock tree synthesis, yeah, similarly, right? So actually, quite some times ago, right? I think one of my former PhD students, he already graduated probably 7, 8 years ago. At that time, you know, when you are doing clock tree synthesis, right, you do have structures, even for data path placement, right? So you have different kind of structures. And if you know that, hey, you know, using machine learning or some pattern matching or some method to identify those structures, and you have kind of, you know, pre-optimized, you know, for those structures, right? You can combine with some random placement, like a conventional clock tree with certain structures. That definitely can also help to achieve much better results. Yeah, absolutely right. This will have a lot of room for improvement. Whether it will make current EDA tools fundamentally outdated, right? I have to say that even current EDA companies, they also have a lot of effort in machine learning. So it's a moving, how do I say? It's also a moving target, right? Okay. The next question. Well, there are quite some questions. How should we do it? Shall I pick someone? Maybe not just in sequential order.
Maybe you can continue the questions, but maybe you can try to answer them a little bit in a concise way, so you can, you know, cover most of the questions.
Okay. All right. Okay. There's a question from Srinath on how the layout of optical IC looks like. Okay, optical IC layout is quite interesting, right? I can refer you to a paper that we wrote even probably 10 years ago now. So optical, you know, you have waveguide, you can bend the waveguide, and the waveguide can even cross each other. So we published some paper called O router, right? Optical router, and oil, we even have something. So essentially, right, but when you cross those waveguide, right, so you will have some loss, but not like electrical layout. You know, you will have short circuit, but optical, you can actually cross. That's pretty interesting. So yeah, that's new interesting problems you can solve. But you know, when you crossing, you will have some loss, right? So the power. So you have to consider other effects, right? There's another question: are the design automation tools for optical photonic IC open source? Not yet. Not, maybe some groups have some open source, but yeah, there are not much open source yet. We open sourced an optical interconnect library quite some time ago. And optical is an interesting research area. It's always future, okay, even 10 years ago. But I think now is much closer to really, you know, in deployment. I think with the electronics, you know, hitting some really hard limit, right? So I think optics is really, I think it will take off finally. Even no, I mean, they already have board-to-board level, maybe chip-to-chip, but you know, ultimately, you know, maybe chip-to-chip or, you know, with 3D IC, right? So integration and even large chips, you may need the optics. Right? How far would the effect this affect jobs in VLSI industry? Especially designs. I think we have to, I guess, coexist, right? I mean, it's like, you know, if it is some very, very routine manual task, probably you don't enjoy doing it anyway, right? You would like to have machine learning to help you. But then there's a lot of other, you know, design space exploration, maybe machine learning is not good at. And also, I mean, at this current state, right, the machine learning for chip design is still, I mean, it's still kind of not, you know, at a very, very high level yet, right? So there are some efforts, but I would also suggest you to embrace the change, right? So it's like office automation before, right? So some job may be lost, but you know, you will find some, you know, you need to continue education yourself, right? Okay, then there's a question of data set for Dreamplace. As I mentioned, right, we don't need a data set, right? Dreamplace essentially is using the hardcore, you know, machine learning solvers. Right? That's a key insight, right? So, but we have some work on data path related to placement. We use some data sets to train to identify what kind of, you know, structures which can do special treatment. Right? But for Dreamplace, the hardcore engine, this deep learning engine. For the placement, okay, the next question from Fadi. For the placement, how often do you need to retrain it, and how much is the resilience to data quality? I mean, I guess if it is a reinforcement learning, right? So they actually can, you know, you don't need too much training data. I mean, you also have, I mean, the Google paper has something supervised learning together with reinforcement learning, right? So, I mean, training quality, of course, depends on, you know, if it is supervised, right? You do need to have, you know, representative and good quality of training data. Okay, next question from Suraj. How do we select a multi-core hardware to execute a given AI-assisted application such as Dreamplace? Yeah, Dreamplace currently is running on GPUs. So, you know, just buy the best GPU. Okay. So, yeah, yeah, it's mainly based on GPU. But, you know, I would say, you know, it could possibly be used in some other computing framework, even TPU, right? So, but if we haven't done that yet, but, you know, it's open source, you can, you know, retarget it to another architecture, right? Next question from Fadi. How do you see the human knowledge added to this flow? I think in this context, right, yeah, definitely in terms of, especially for analog IC designs, right? Analog IC design indeed has a lot of human knowledge, right? So the symmetric structures and, you know, like the people even sometimes do like, you know, other like, you know, structures, right? So you have signal flows, right? So those intelligence could be used, right? Common central, right? So yeah, how we can kind of learn from humans, and yeah, we do use human knowledge to generate some good layouts, and then which can help us to build our learning model, right? Okay, so all right, next question. How realistic is the 24-hour turnaround time targeting? Well, I guess, yeah, I mean, this is a kind of very big kind of dreams, right? Depends on really how complicated your design is, how large your design, and how do I say, how high the performance PPA target you are targeting, right? So when DARPA first set this goal, they say, hey, you know, you can have a 2 times PPA degradation. Actually, for the ADCs that we tapped out, you know, our entire thing runs in like 1 minute. You know, of course, it's not the largest, the biggest SoC, right? So again, right, depends, you know, for like a very state-of-the-art Apple chip, I think it's pretty hard, right? Okay, they do can afford, you know, to hire hundreds of engineers. You know, you talk about the year. I mean, to architect this and different supports, they, you know, optimize all this, right? But if it is not so performance, you know, like high performance, like Apple's chip or NVIDIA's, right? So you could still possibly do it 24 hours turnaround time. Yeah. All right, last question here. How can one change the floor plan layout generated by Magical? Okay, so this is a great question. So yeah, we generate this, you can still manually tweak it, right? We also actually have, with my collaborator and former PhD student, Yibo Lin, right? He is now teaching at Peking University. We have something which, oh, I think hasn't been published, will be published at this year's DAC, right? But you can send me an email or contact Professor Lin, right, for a preprint, right? So basically, we can also have an interactive mode of Magical, right? Which, you know, with certain human, you know, human interaction, right? We can use core Magical with certain human interaction. So yeah, we actually have that capability, right? All right, I think that's all the questions I see now. So.
Thank you very much, David, for taking the time to answer all these questions. And it was a very fantastic experience. So both a very good talk and lots of discussion and answering the questions. So I think this is the best of, let's say, the outreach that we could hope for. And thank you very much for doing that. And thanks everyone for attending the talk. So please stay tuned for the next presentation in the list of a distinguished lecture program of CEDA. The next one will be on July 15th, Thursday. So basically, I guess 3 weeks from now, same time. And this is given by Rajiv Joshi from IBM on predictive analytics in machine learning for VLSI circuits. So lots of interesting talks related to AI and machine learning. I'm sure many of us will benefit from these talks.